I'm talking about partitions. That's really the topic that I would like to try to address right now. But this is a good example, and I just want to spend a little bit more time on this example of algebra with things that are other than numbers. Okay, so you certainly have seen algebra with things other than numbers would be vectors, for example. Well, you can do algebra. You can do algebra with functions too, right? So once again, but ultimately they are too far, too close to numbers in order to just say that that's something crucially different. This is also very close to numbers, but you can see how things have changed. It is algebra, but there are only two numbers. So no matter how you look at it with the every time you do algebra, you actually have infinitely many numbers available. Even in first grade. Well, in first grade, you're able to count until 10, and that you may have a feeling that there are 10 numbers only. In but you know, you already add 5 and 7. You already realize that there are more numbers. So it doesn't live long, that impression that the numbers, there are not too many numbers. You realize that there are infinitely many numbers, and that's probably the way how you first time you face infinity, probably. And this is definitely not infinite. So that's the main difference between algebra that you have seen, numbers, functions, vectors, and algebra of these numbers. So pretty much 0 and 1. But they are not really 0 and 1 in the sense of being actual numbers, because the algebra is different. If the algebra is different, can you really say that they are the same numbers? Is it really 0 if is it really 0 and 1 is it really 1 if you add 1 to 1 and you get 0? Well, that maybe not 1 after all, but maybe it's something else. So we'll just use the notation for convenience, but otherwise it's something different in nature. So it is, and what we're trying to say here is that over here that we're talking about altogether all the numbers that are even or all the numbers that are odd. Okay, so and then we have algebra on those on the two sets the two sets that partition the integers. Okay, so addition, then the multiplication works out similarly. So 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. Okay, so furthermore, you can arrange them in the table of addition table and multiplication table just to confirm that we have covered everything. So and we have covered everything means simply that you do not is what happened to you in first grade is not going to happen. So 5 plus 7 is larger than 10, and you don't know what to do with it. Okay, so let's just make sure that is the case, and we did. So 0, 1, 1, 0. Okay, so if you start with two numbers, you do the algebra, you still have those two numbers. Okay, so this is the addition table, and then I have the multiplication table, which is different, as you'd expect, right? 0, 0, 1. Okay, so multiplication table and the addition table. Okay, so all right, so these are special kinds of numbers that with a whole set behind them. Just before we continue on with this, I want to take us back to propositions and logic of propositions and conjunctions. The true false, and what happens when we combine them with the and or. We talked about that. I don't think we ever formalized it in the algebraic way, and that's why a good time to do that now. So, for example, so starting with and, so true and true. Well, this true and false. Is it true or false? It is false. Can you explain why?
Because 1 plus 0 equals 0.
Well, no, that's not. We will go through the wrong order of things. Cart and the horse. So I want to establish this before, and then make that connection by that you are alluding to. So why true and false gives me false?
Because false is dominant, like takes over the truth. Like the false, you have false in your statement, so it has to be false.
Well, kind of, yeah, yeah. So remember what and means. It means that both of them have to be true for the whole thing to be true. That's the way we did it a few times, mostly with algebra. But remember, conditions are, if you have conditions of your theorem, then they have to be, all of them to be satisfied in order to go on and draw the conclusion. So yes, indeed, you cannot have true and false will be false. False and true is once again false. True, false and false is still false. Okay, or now the opposite, right? True and true is certainly true. True and or false. For the whole thing to be true, only one of them has to be satisfied. So it's true. And false or false is false. Yeah?
On the and, why isn't the false and false true?
Well, no, false and false.
On and?
False and false is false, yes. Or false. False or false is false, yes. Okay, well, actually, there is another way to, yet the third way to look at it is the set theoretic interpretation of this. So what is the set theoretic interpretation of the first table? Remember what true and false correspond to? Empty, non-empty. So the intersection of no, that's quite work the right way. Well, forget it. I don't think it's going to work. I didn't really think it through. Okay, so let's just let's make up tables. These are algebraic operations on propositions, on propositions, yes, and we have done that several times. How these conjunctions from two propositions create a new one. Okay, and this one, however, only refers to one aspect of that, and that whether or not those three propositions true or false. And this is the relation which is very transparent, but I want to interpret it as in a more algebraic way. So I will be doing the true-false. Once again, not thinking in terms of zeros and ones. Let's just go with what we see. So so if I go with and, so well, you can guess that I should probably, well, anticipating what we're going to do is probably not true-false, but rather false-true, because false is 0 and true is 1. Okay, let's see if it matches what. So true is true. The other two are false and false, and this is also false. Okay, and the other one is the or false true, so false, true, and true. Okay, so if you now look at the tables, what do you see? So, well, we have two tables here and two tables there. What do you see?
That and is equivalent to multiplication?
And seems to be, and seems to be equivalent to multiplication if, specifically, this is what is being suggested, if you do what? What's the correspondence? Right, 0, false is 0, so false is 0, and true is 1. Okay, so that is the, well, That's what you got. Just one by one you can replace them. What about the other one? Well, I mean, it doesn't correspond to anything actually. No. I mean, if you could try. I mean, it's not entirely true, is it? Can you, maybe not, this is a straightforward connection that I made. So once again, false replaced with 0 and true replaced with 1. Okay, so, so there seems to be no connection for the other table at the bottom. Or is there? Well, you just flip it. You just flip it. Remember well, the relation between true and false is the negation, and you remember how negations correspond. Remember those formulas for negation of what happens to conjunctions under negations, and they flip. Remember this, a be negated is what? What? With flipping the conjunction. So as you can see, that is the relation. You can actually go straight here. You just negate, replacing true with false, false with true, and you replace and with or. Okay, and so you actually do have, I mean, replacing true with false. That's quite a statement. I'm not saying that true is false. That doesn't get me wrong. But replacing true with false does in fact replace change the algebra from and to or, and vice versa. Okay, so we can go back and forth, which means that we still can connect to algebra. It's just, back to that table at the top. Okay, so just these tables are good to keep in mind, and that's called Boolean algebra. Boolean. Okay. In the meantime, we're back to to something that is a big topic, and that is it's called equivalence relations. Okay, and equivalence relations allows us to simplify things a lot by creating big sets from many elements, and then treating those sets as if they are elements themselves. Okay, so that we just did it over here. Okay, so we had we have infinitely many numbers, but then we split it into two, odd and even, and then we're treating this P and Q only as if they are quantities themselves, or at least they are not sets as such anymore. They are elements of a new bigger set. So what the point I'm trying to make here is this: we are proceeding to this P comma Q. That will take some time to get used to this, what I just wrote here. So what are you seeing here? P comma Q. No, it's not. They're not the same set. The P and Q are, so P is odd, Q is even. Okay, so
Together they make up a set?
yeah, this is all here, yes. But I want you to recognize what's new here is the braces. What do the braces indicate? Braces and a comma. Well, what does this tell you? 1 and 2. What is this? 1 and 2 meaning is a set that consists of 1 and 2. Okay, now that's old. Now new is we have formed a new set, but its elements are sets. Okay, so that's the going to the next level of abstraction is the sets are abstract enough, and then what we do about too is to start recognizing that sets could, if you have several sets available, you might put them together and then form a new set of sets. Okay, so seems complicated and maybe unjustified, but I hope we will justify it here. It's almost done here because we already that new set of sets is in fact something that, well, it's small, unlike Z, which has infinitely many numbers. This set, even though it's a set of sets, but how many elements does it have? Only 2. Okay, so that certainly makes life easier. The algebra also, look at it, the algebra is very simple. So we not only created a new set, we also created an algebra on that set. So it's, once again, the elements of a set might look complicated, but the reality is there are only 2 of them, and which makes certain things very simple, including the algebra that we already have. We have, in fact, both addition and multiplication, and incidentally, I forgot to mention it, but if you can certainly think about commutativity and associativity. Remember those properties of algebraic operations, as well as distributivity. And maybe a few more properties of algebraic properties that that satisfy for numbers. They still satisfy for this algebra. And the verification is very easy because there are only 4 ways to add and 4 ways to multiply these numbers. Okay, so but this is the crucial part is forming sets of sets, and we just as similarly we made that exact step over here. So if I put true in T and F, once again T stands for all the true statements and F stands for all false statements. So it's like dividing the whole universe of statements into only 2 classes, those that are true and those that are false. Okay, and then once again turns out there is certain algebra between them. Okay. So so let's take this in a more careful way, and starting with the so this is a big idea, big construction, and it has applications throughout mathematics. But it's a good idea just to start with something more tangible, and that is the just one step up from this, and that is just the remainders. Remainders, based on the remainder theorem, we could deal with numbers that, instead of dealing with all the numbers in algebra of all integers, we will deal with the algebra of the remainders. Okay, so this is algebra of remainders under division by 2, 0 or 1. So we throw out the part that is divisible by 2, and then we're left with a 0 or 1, and then turns out the algebra works out just fine. So let me make that next step. Okay, so already did it. So given these 2 definitions that are crucial, so given a set X, any set, a partition of X is a collection of subsets of X. Could be finite, could be infinite, but let's start with finite. So say P1, Pn, such that first they are disjoint. In other words, disjoint pairwise. So Pi with intersection with Pj is empty if I is not equal to j. Okay, so disjoint. And just like we started with the example of partition when there are only 2 sets, and one of them was the even and the other one was odd. Okay, so and that's an example of that. But the first example, they certainly first condition that they cannot intersect. Second one, they make up the whole space. They make up the whole set. That is X. So P1 union P2, Pn is equal to X. Okay, so certainly you can divide in a number of ways, partition, and so once again, example is X is equal to Z, P1 is equal to all odd numbers, P2 all even numbers. Okay, so there is no need to do anything else for number one example. However, once we start moving up, X is equal to Z, I could go with, say, P. And instead of looking at odd and even numbers, divisibility by 2, we'll look at divisibility by 3. Okay, and then we have P1, P2, P3, or P3. So will be divisible by 3. Remainder 2, remainder, well, in chronological order 1 and 2. Okay. So so divisible by 3. Divisible by 3 means that remainder is 0. Here remainder is 1 and the remainder is 2. Okay, so so it's once again every number, every integer, either one or the second or the third. Okay, one of the three, and they do not overlap. Okay, so in order to continue on with this, we need to state the remainder theorem just in case. So the remainder theorem, the one that we proved, remember. Theorem. Okay, so so any integer, for any two integers, remember how we put it, for any integer x. So I said it slightly different. Remember, it actually started with for any integers a and b, you can have a is equal to qb plus r. Remember, so for any a and b, that's how the remainder theorem starts. But now we are taking a slightly different angle. So I started slightly different. So I will be concentrating on the divisors separately from everything else. So I'll put here, I'll call it for any integer, positive integer, n. So we'll be doing division by n, larger than 1. Okay? So division larger than 1. And then, in fact, once again, when you state the theorem, you have to state it in such a way that it would be clear what you're driving at. And what we're driving at is to fix that n and consider divisibility by n separately as a separate statement. So let's say given an integer. Given integer n larger than 1, and now we do division of any number or other integer x by n. Then for any integer x, they are p and q and n are remainder, okay, such that x is equal to q n plus r, and r between 0 and n. Okay, so that's roughly what we stated. We proved with the Euclidean algorithm. There is an important part missing for our purposes. this is an existence theorem. There is a representation of X in this manner. Whenever you have existence theorem, it should be accompanied by a question of what? What? Uniqueness, right. So why do we care? So that we could, everything else, it's not going to work. Any of this is not going to work if that representation is not unique. So that's the second part. So this is the first part, and the existence part, and the second uniqueness part, this representation is unique. In other words, so, well, how do we translate this representation? Representation is unique. How do we translate it in a more precise way? Let's expand it. So what do we say? How do we say it? Remember about limits? So to say the limit is unique isn't really much. You have to be specific to say, well, what do we mean by uniqueness? Remember what we discussed it earlier this week?
You're just asking what unique is?
Yes, what uniqueness means.
One answer? I mean, it's...
Well, one answer, yeah. Right. So one answer, so we indicated part one, we indicate that there is an answer. Okay? Now we want to say that there's only one answer like that. So how do we put it in a more precise way? Because we're going to prove it.
So you can't just say it's unique? That's not the right way to do it?
No, it is right. But when you're going to prove it, how are you going to prove it? It's just unique, and that doesn't really mean it.
There's one answer?
Right. But you have to be more specific about it. So how do you show that there's only one answer? You show that there is no other. And if there is one other, then what? Then it's the same. Okay, so that's the uniqueness. It means that if there is another one satisfying the same equation or whatever, then it is the same. Okay, so usually just to say that, say equation, this equation has a unique solution. It means that, well, if there's another solution, it is the same. So there's a solution set, and it consists of one single element. So specifically, this is how you put it. You say that if Q prime, R prime satisfy the same condition, so X is equal to Q prime n plus R prime. See how I paired them up? So I am imagining another number, a pair of numbers as a matter of fact, satisfying the same conditions. And then I say, well, that's the same. Then R prime, Q prime is equal to Q, R prime is equal to R. Okay, so with the limits, it's one number and it's easier. So you say, well, if this number also satisfies the definition of the limit, then it's the same number. Okay, similarly here, if I have another quotient and another remainder, which means that they have to satisfy this equation, then it is the same. These are the same pair of numbers. Okay, so that's how you clarify it, and it's really necessary if you actually want to prove it. So since we proved part one with the Euclidean algorithm, so it was in fact constructive, which means that we actually were able to find R and Q. Okay, but it does not of its own indicate that there is no other way to construct them. Okay, so we have to, actually what is stated in part two, we have to just go straight ahead and prove it. So we have two pairs of numbers, so X and Q are fixed, X and N are fixed, and now we have two pairs, Q and R, and we have to prove them. So it's not really that complicated once you write it out. So this is what we know. They satisfy the same equation. They are also, they satisfy these two conditions with extra conditions that I skipped, but it certainly will come up. These I did not yet use. But you can guess what's supposed to happen next. What do we do with these? We could set, yeah, we set them equal or we subtract, whatever, it doesn't really matter. We have to combine them somehow. So I like to subtract them. So it will be 0. And here what am I going to be doing? I will be factoring. So it will be q minus q prime and plus r minus r prime. Why am I doing it this way? Because I'm pairing up those numbers that I'm supposed to prove to be equal to each other. Okay, so you can see how their q is paired up with q prime, r is paired up with r prime. Same with the limits. When you do prove the uniqueness of the limit, you do pretty much the same thing. So you suppose that exists, and then create an equation that will somehow work you towards the inevitable conclusion that those numbers are equal to each other. So at this time, what do we have here? Okay, so let's analyze this equation. So it's actually similar. Notice that it's very similar to the equation that we started with, except on the x equal qn plus r. It's very similar, right? Because you have some kind of r on the left, you have some kind of q, you have n. It's all there, except on the left we have 0 rather than some kind of number. So, okay, so what do you see? Well, here's an idea. Investigate the divisibility by n of this number. Is this number divisible by n? Look at the left-hand side. Yes, it is, because on the left it is 0. 0 is divisible by any number, so yes, it is. It is divisible by n. Okay, so that's on the left, so 0 is. Okay, now look at what's on the right. What do you see on the right? Say it again.
Q minus q prime will be divisible by n.
No, not q minus q prime. Q minus q prime times n is divisible by n, right? So we notice that q minus q prime times n is divisible by n. Okay, great. So 0 is divisible by n. The first term on the right is also divisible by n. So what do we know? Remember about divisibility? Well, I could write it, well, how about this? R minus R prime is equal to negative Q minus Q prime n. Okay, so what does it tell you?
R minus R prime has to be divisible by.
Yeah, that's right. So you can think about the fundamental theorem of arithmetic or just divisibility. We conclude that R minus R prime is divisible by n. Okay, so what's the conclusion? And at this point, we got to bring up those two extra conditions at the top. R and R prime lie between 0 and n. So I make an observation, but R is between 0 and n. R prime between 0 and n. So what? Well, the difference will lie between 0 and n. Okay, so match up those two statements. What's the conclusion? A number that is less than n is divisible by n. What's the conclusion? No, it is just one number. R minus prime, I'm looking at it as just a single number. It is an integer between 0 and n, and it is divisible by n. What can you say about this number? A number less than 3 divisible by 3, what is it? 1 is not, no. The answer is 0. You cannot be divisible by a number that is less than the... You cannot divide by a number that is larger than that number and be in hope to have a 0 remainder unless you start with 0. Okay, so like I said, if n is equal to 3, and you're looking at 0, 1, and 2. Okay, so, you know, it's like a fraction. Well, a fraction with the denominator less than the numerator less than the denominator, right? So it's like r minus r prime divided by n. So we know it's less than 1, right? But larger than or equal to 0. So an integer that might explain what's going on. So you start with an integer, and then what you discover is that it is then you divide by n, which gives you a fraction, and that fraction is less than 1. So a fraction less than 1, but it's supposed to be an integer. R minus r prime is divisible by n, right? So then this is actually supposed to be an integer. An integer between 0 and 1. What's the integer between 0 and 1 that does not include 1? Only 0. So indeed, r minus r prime is equal to 0. So r is equal to r prime. And then, the last part is about q and q prime, where that is also not really hard to find out, because q is equal to, or q prime rather, equal to, what is it? X minus r prime divided by n. Okay, and this is r prime is equal to r, so it will be x minus r divided by n. It is equal to q. Okay, so you have demonstrated that both of these numbers are the same, both r and r prime is equal to r, and q prime is equal to q. Okay, so it's based entirely on what we know about divisibility and very basic things. So even though we're looking at remainders, but really we were able to use only actual divisibility, not divisibility with a remainder, and that's how you bring your solution into this your knowledge of divisibility into a statement about a remainder of under divisibility. So when there is no divisibility, and then you still can say something about what's going on, and that is that there is a representation proven previously, and that representation is unique. Okay, so then this equation that we have here is one and only, and we could, which we tried to do already, we can replace x with r. Okay, so for example, when n is equal to 2, then r, the only two values for r are 1 and 2, 0 and 1. Okay, so and that takes care of all possible integers in the universe. Okay, so we'll just resume next time.